Welcome to the structural analysis course. So if you recall last week we have started the new module, that is deflection and slope calculation of a beam. So till now we have seen the derivation of beam equations starting from scratch, and then in the last class we have discussed the first method to calculate the deflection and beam using double integration method. So what is double integration method? If you recall, whatever equation we have derived, beam equation, if you integrate the equation into two times, you will get slope and deflection. So after first integration you will get the slope, and again if you integrate the slope equation, then you will get the deflection equation. So this method we have discussed in the last class. So today we'll discuss another method to calculate the deflection and slope in a beam, that is using the moment area theorem. Now you may ask why already we know, right, what is the method of calculating the slope and deflection, and why we need another method to calculate the same thing. Because in a structure the supports are different, right? So one may be fixed support, another may be hinge support, or different support conditions, different types of loads are acting on a structure. So depending on the situations, one method may be easier to solve. Okay, so that's why we have to understand few more methods. So all methods basically we can calculate the slope and deflection, but each method has some advantage and disadvantage also. So some method may be useful in particular condition itself. Other loading condition, if you use the same method, then it may be troublesome. You may have to use another method. So that's why we'll see in this course, basically we'll see the four types of method to calculate the deflection and slope. So in the last class we have discussed double integration method. This class we'll discuss the moment area method. So in the next class we'll discuss another method to calculate the deflection and slope. So essentially all the methods will calculate the slope and deflection itself on a structure. So let's discuss first what is the concept. So if you see, this is the arbitrary beam. Arbitrary beam is a simply supported beam, right? One end is hinge, another end is roller, and some arbitrary loading W is acting on it. And this small section, if you call it, then we have derived the equation of our of a beam. So what is the equation we have derived till now? If I write you here, so it will be y d square y. So the same equation basically we'll use here also. So d square y dx square is equal to m by ei, right? So this is a beam equation we have derived in the last classes. So this is a beam equation. So from here, if you integrate one time, so this equation, what you will get? So one time integration means we'll get the dy dx is equal to integration m by ei into dx, right? This is the first integration, and one more times integration, if you do it, you will get y equal to double integration m by ei into dx, right? So this is the things we have discussed in the last class, that is using the double integration. Two times if you integrate the equation of beam, you will get the first integration, you will get the slopes, next integration you will get the deflection. So the same concept basically will use in this method also, that is moment area method. So if you see this equation, right, so this d theta so basically from here only we can compute what is the slope. So dy dx is what? Dy dx is nothing but your theta, right? That is the slope. So this equal to, we can write it in that fashion, right? M by ei integration, anyway, m by ei into dx. So what is m by ei? So m by ei is a moment by ei is a constant into dx, right? So if you just if you just convert, m is basically the moment diagram, right? So this is a load is applied on a beam, and after application of this load w, so this is the thing, this is the moment diagram you have, right? Already we know what is the moment diagram. So how to calculate, how to draw the moment diagram, we know that. So this is a moment diagram for this beam. So this is arbitrary load w acting, so this may be the moment diagram. So moment diagram means m diagram. So now if you divide m by ei, so what already you know the moment diagram means all the coordinate values you know, right? So this divided by ei is a constant, you will get some value, right? E is modulus of elasticity and I is the moment of inertia. So ei is some value you will get. So m by ei, if you draw the m by ei diagram, so m diagram already we know, moment diagram we know. So moment diagram divided by ei, you will get m by ei diagram. So this is M by EI diagram, right? So dy dx equal to, what we can tell is M by EI into dx. So M by EI is nothing but this height, right? This height is, we call it M by EI into distance, dx is this much, right? So that is theta. So that dy dx is theta equal to M by EI into dx. So now if you consider this small section here, so this small section's width is dx and height is M by EI, then what is the area here? What is the area inside? Area will be simply width into height. So height is M by EI into width is dx, right? So M by EI into dx is nothing but the area here. So and which is nothing but dy dx theta. So theta is equal to simply area under M by EI diagram. So this is the area of M by EI diagram. So area under M by EI diagram will basically give you the theta. So this is our first theorem, that is moment area theorem. So the change of slope between any 2 points on an elastic curve is equal to the M by EI diagram between these 2 points. So what is the slope? If you want to find it out, what is the slope change from this point to this point? So here, if you consider 2 points, one is, left side of the small section dx, another is the right side of the small section of a dx, right? So change of slope can be easily computed simply if you draw the M by EI diagram of this entire beam, and if you find it out the area here inside, then that will give you the slope difference between the 2 points. That is our first theorem. The change of slope between any 2 point, it may be any 2 point on a elastic curve, is equal to the M by area under the M by EI diagram between those points. So simply, how we derive this equation, already we know this equation, right? Dy dx equal to M by EI into integration M by y into dx. So M by EI is basically height and dx is the area. The dx is the length, right? So M by EI into dx is nothing but area of M by EI diagram. So this area. So simply if you draw the M by EI diagram of any beam and find it out the area inside that, and then easily that area will give you what is the slope difference between the 2 points. So this is our first theorem. And our second theorem is what? So from here only, so this is what, so y equal to deflection is double integration M by EI into dx, right? Double integration, so I just missed one dx. So first dx came from one integration and another dx will come from another integration, right? Double integration, so 2 dx will come. So from here, what you can write? From here you can write M by EI into dx. So this part already we know. This is the area under M by EI diagram, right? This multiplied by again dx. So this is area into distance again. Dx is distance, right? So that's why this is also a moment of area. So this one is area. First one, M by EI into dx, is nothing but area of M by EI diagram multiplied by distance will give you moment of the area. So that's why the method name is moment area method or moment area theorem. So basically we are finding out the moment of area, and which will give you the y deflection over. So in this method also basically we are finding out the theta and y, right? So theta is nothing but this one, already we saw, simply area under the M by EI diagram. And what will be the y deflection? Deflection is nothing but the moment of that area. So this is the area. If you take moment of that area, you will get the y deflection. So that is the theorem 2. Theorem 2 is the vertical deviation of a tangent point at A on an elastic curve with respect to the tangent extended from the another point B equal to the moment of the area under M by EI diagram between these 2 points. So for example, you want to find it out, what is the deflection difference between A and B, right? A also has some deflection, B also has some deflection after application of the load. So how much is the deflection difference? How much is the difference between A to B? So that actually you can calculate using the moment area method, using this expression. So let's solve a quick example, then only this entire concept will be clear to you. So the procedure for analysis here is, first we have to draw the M by EI diagram. What is M by EI diagram? That is nothing but you have to first draw the moment diagram of a particular beam. So once you draw the moment diagram, you just divide it by EI and you will get the M by EI diagram. So once you draw the M by EI diagram, Next, you draw the elastic curve. Already we know how to draw the elastic curve. And then lastly, you apply the moment area theorem. That means simply area under the m by e diagram will give you theta, and moment area into distance, that is moment of the area, will give you the deflection of a particular point. Very simple. So you have two things. One is you have to draw the m by e diagram, and then the area under any two point in the m by e diagram will give you the deflection, sorry, slope, and the moment of that area will give you the deflection from the point. So let's solve a problem here. This entire concept will be clear to you. So let's consider what is the question here? Question is determine the slope at any point B and C. Okay, the slope at any point B and C of a beam shown in the figure. So this is a figure. You are asked to find out what is the slope at B and C. So this is a cantilever beam, right? Cantilever beam means one end you have the that fixed, another end is free, and the 2K load is acting on it, right? So after application of the load, what will happen? Your beam will buckle. So this is a buckle shape. So something you can draw here. This is the buckle shape, and 2K is acting here. So our question is you have to find it out the slope at point B, slope at point B, and point B, as well as the deflection at, calculate the moment diagram. So this is the moment diagram, right? So our first job will be to draw the moment diagram. So after application of this load 2K, now what will be the moment? So moment diagram will be simply in a triangular shape, right? So moment is what? Force into distance, right? So if 2K is acting, how much moment will be generated at the end A? At the end A, moment will be generated. 2 force is 2 into distance is 30, right? So 2 into 30 will be 60. So at this point, at the support A, you have the 60. 60 will be the moment generated at this point. So if you see at the midpoint, how much moment will be generated at the midpoint? So midpoint will be 2K into distance. Distance is midpoint is 15, right? This side distance will be 15. So midpoint will be 2 into 15, that is 30. So here it is 30, whereas here it will be 60, right? At the support you have the 60. And basically this diagram is a m by ei, right? So whatever moment you got 60, you have to divide it by ei, then only we will get the m by ei diagram. And our main objective is to draw the m by ei diagram, right? So this is simply, first you draw the moment diagram, and whatever coordinate you will get it, you just divide it by ei, then we convert into this diagram into m by ei diagram, right? So up to this will be minus 60 by ei, and this is midpoint 30, this height is 30 by ei. So this is the m by ei diagram, right? So now what is the question? Question is determine the slope at B and C. So at this point, what is the slope? And at this point, what is the slope? So let me just draw the elastic curve. So elastic curve of this beam will be something like that, right? So this is a deflected shape of this beam. So you have to draw. So if you draw a tangent here, so this tangent, how much angle it makes with the horizontal? That is theta C. Similarly, if you draw here a tangent, and this tangent, how much angle it is making, that we call it theta B. So our question asks to find out what is the theta B and theta C. That is a simple question, right? So, and this m by ei diagram already we have drawn. So how we have drawn? Firstly, we have drawn the moment diagram. That is, it will be simply triangular shape, right? Why triangular? Because the intermediate there is no moment, only single moment, single there is no moment, only single force is acting. That is 2K at the tip. So whatever the moment you will get here, so it will be force into distance, right? Force distance is 30 feet given 30 into 2, you will get the 60 by ei, is because we are drawing the ei m by ei diagram, right? This is the diagram, we got it. So our first we'll calculate what is the slope at theta b, right? So what we got from the theorem, so moment area theorem, what we got, simply area under the m by ei diagram will give you the slope difference between the both the points. So here you have the 2 points, right? One is a, another is b. So our main objective is to find out what is the theta b. What is theta b, that we have to find it out. So here, what is the value of theta? Slope at this fixed and support. So fixed and support, already we know that fixed and support theta is always 0. So if you find it out, the slope difference between these 2 points. So here it is anyway 0. So here you will get what is the value of theta b, right? So how to calculate the slope difference between these 2 points is nothing but simply area under the m by ei diagram of this point, 2 point. So this point, so this is entire area, this shaded line, right? This blue line, blue shaded line is nothing but the area under the m by ei diagram. So if you calculate what is the area here, that area is nothing but the slope at b. Very simple, right? As per this equation, as per this theorem. So what is the area here? So this entire, this blue shaded area. So this is a trapezoidal shape, right? So you can divide it in two parts. One is this rectangular area and another is this triangular part area. So you just divide this entire area into two parts. One is this rectangular part, another is this triangular part. So how much is the area of rectangular part? So simply the width is 15 into height. So height, this height is how much? This height is 30 by EI. So 15 into 30 by EI will give you this much area. So that's what we have done here. So 15 into 30 by EI. So this first part is nothing but the area because of this rectangle. Now what is the area here? This triangular area. Triangular area is simply half into base into height, right? Half into base is 15. So this is the equation we have written. Triangular area. So half into base is how much? 15 feet is given. So 15 into height. So how much is the height? Height means this much height. So this much height means total is you have the 60 by EI and this much is 30 by EI. So what is the net here? Net also you have the 30 by EI, right? So 60 by EI minus 30 by EI. So this is the height. So this one is the rectangular part, this part, and this one is the triangular part. So if you just combine both, you will get the final theta b. So final theta b you will get, this is this much radian, right? Theta b is a slope, right? Slope is you have to convert into degree or you have to do it into radian. So that much is the radian, that much is the slope at theta b, right? So now the question asks to find out the slope at b and c also. So at the c point also we have to find it out. So C point means now so we know what is the slope at this point. This point is 0. So if you find it out, the slope difference from this A to C, then you will get what is the theta C, right? So theta C will be simply area under entire triangle, because we are finding out the slope between A and C. That means A and C, M by EI diagram, how much is the area? This entire triangle area, right? So entire triangle area is how much? Half into base is how much? 30. Half into 30 into height. Height is minus 60 by EI. Minus 60 by EI. So this is the entire area of this triangle. Okay. So from here you get what is the value of theta C. So theta C is now you computed also. So theta B and theta C both computation is done. So slope both you have computed. So now if the question asks what is the deflection also at the theta B and theta C. So this is the slope computation is over. This is one part is over. Now if question asks what is the deflection at B and C, means after application of 2K some deflection will takes place, right, at B and at C. So what is this deflections? So what is the value of that YB and YC deflection at B and C? So using moment area method, simply you know the area, right? This area already you know, theta b into distance. If you do it, moment area, if you see last theorem 2 we have discussed. So whatever area we have calculated, so that area if you multiply with the distance, right? So if this radian, this value, if you multiply it with this distance 15, then you will get what is the deflection at this point B. Similarly, whatever value you get, this if you multiply it with the distance is total 30, you will get what is the deflection at C. Means moment, you have to calculate moment, that area's moment. So like that actually you can easily compute the slope and deflection at any point in a beam, right? So this method is very simpler. How? Because the any beam, arbitrary beam is given to you. First step will be draw the moment diagram. Moment diagram drawing is very easy. So once you draw the moment diagram, you divide it by EI. So M by EI diagram you drawn. So now you just find out how much area inside the M by EI diagram. That will give you the slope, and find it out area into distance, right? Distance from where you want to find it out. The distance will give you the deflection. So using this method, so now if you see instead of earlier method means you have to integrate the equation 2 times, and then you have to apply the boundary condition, then only you will get the theta and y, theta and deflection. But in this method, simply you draw the moment diagram. So once you draw the moment diagram, then you just simply find it out the area inside the moment diagram. That area will give you directly slope. There is no computation required. Directly you find it out area, you will get it will give you the slope directly. And then if you multiply the area with the distance, then you will get the slope at any point and deflection at any point. So this is the this method, that is moment area method, right? So this method is useful when you have one end cantilever beam, right? Because this method basically will give you how much slope difference between 2 points, or how much deflection difference between 2 points. So if you have one side cantilever beam, means you know already slope at this point is 0, deflection also at this point is 0, right? So you can find it out area with respect to this point, any portion you can do it, because here you know it is 0. So whatever you will get area, that will be particularly because of that point. So when you have one end cantilever, I mean one end fixed support, that time this method is very much useful. You can easily compute what is the slope and deflection. So we have completed this second method also. So next class we'll discuss another method to find it out the slope and deflection. Thank you.